Today, we are talking chapter 23, and it's kind of a lot of building on what we just talked about, right? There's going to be a lot of similarities. I'm going to kind of recover a lot of the topics that we just talked about last time, but I think it's a worthwhile endeavor to go through it again just to make sure maybe a slightly different explanation the second time around, something like that. Maybe something sticks a little bit better. Because realistically, describing fields and how we discuss fields and the forces that arise from fields are going to be a lot of what we do from now on. Right? It's going to be a lot based on this, the idea of the electric field and later the magnetic field and all of the different things that we can do with those things. We're just going to grow and grow and grow on these topics. And so it's worth going over again, at least in my mind. So, kind of remembering what we had seen from when we first started all this stuff. We first started by talking about Coulomb's law, right? Which was essentially almost like gravity, but for electric charges instead of mass, right? The equation looks pretty much identical, though. It's k q1 q2 over r squared. But when we were talking about that the first time, we basically said, okay, forget about the fact that it's a vector for a little bit. Find the magnitude, right? Put absolute value signs around everything. Find the magnitude, then deal with the direction later. Right, and then we said basically, okay, well, we know that if they are like charges, if it's positive, positive, or if it's negative, negative, then in cases like that, they're going to be repulsive towards each other. If they are opposite charges, positive and negative, then they're going to be attracted to each other. That's a little bit different from gravity, but we said basically, remember that rule. Don't bother about the vector part. Come up with the vector part after you've already solved out the magnitude, find it on the picture, and call it a day right there, right? And we just wanted to do that really to kind of give you guys a little bit of a ground to stand on, to deal with these things in the first point. Then last week, we started talking about electric fields that basically said, hey, you don't need a second particle for an electric field. The electric field originates from any charge, and it's kind of like the force waiting to happen. And I'll get back to that in a second, but we described the electric field from a point charge as kq over r squared times r hat. And r hat was probably the funkiest part of this entire thing, right? First, we had to worry about the fact that there's no absolute value signs anywhere. We just kind of jumped in with sticking with vectors. But r hat was really the sticking point. And I've got a thing on that as well. But r hat is essentially going from your charge to your point. That's the direction that you're going, and then whether it's positive or negative might flip that around. Just like when we were dealing with forces, we can still deal with this thing in terms of only magnitude. That will still get us to the correct answer, right? That's not a big deal at all. You can just take the magnitude of each thing and find the direction afterwards from the picture. Totally fine. But while we're doing a lot of these things, it might be helpful to draw up pictures, right? We're talking about finding stuff off of pictures so often, and the number of pictures that we're going to get from the problems, it might be helpful to be able to either create these pictures or to understand when they're given to us. There are two different kind of schools of thought when we're drawing these pictures. The one on the left is basically saying, okay, take a bunch of different points, the length of the arrow tells us about the strength, and then you draw it in the direction that it's going. So for any positive charge, that's radially away. For any negative charge, that's radially inward. The other one is a little bit simpler. All we really have to do is draw a bunch of field lines from the point charge in the first place, and then we don't draw a bunch of extra stuff outside of that. We just settle with that, and then we basically say, okay, where it is more tightly packed, so right around the charge, where the lines are closest together, that's where the strongest field is. When we're more outside, when the lines are farther apart, that's going to be a weaker electric field, right? And then same deal, positive and negative. So r hat was probably the trickiest point about the last slides, and it might still be the trickiest point about these slides as well, right? Because it's kind of a tricky concept if you're not used to seeing it. R hat is not a unit vector quite like I hat and j hat, because r hat doesn't really care about what direction it's going in. R hat's a variable unit vector. It's allowed to go in any direction, and really what it's telling us is that for a point charge, it's radially away. So, and it's not set in one particular value anymore because E is not just one particular value. Remember that the electric field is surrounding the particle. It has quantities and directions at every single point in space, right? If I have my electric field here, it's not that I am limited to only the black dots. I have an electric field, a quantity and a direction at every single point from right outside the particle out to infinity. So to just limit ourselves to one single direction or something like that, really, it doesn't make any sense. R hat is there because it allows us to figure out, okay, what is the direction at this particular point, knowing that we could be pointing in any direction. So the way that we would find that from the picture is to start from our charge, to draw a line out to the point where we want to calculate the electric field, draw it out a little bit past that, and draw an arrow on the end. And that's how we get R hat, at least from the picture, right? The other way that we can do this is we have this surefire equation, R hat is equal to cosine of theta times I hat plus sine of theta times j hat. But there's a caveat to that. Theta is always from the positive x-axis. That's a necessity. If you want to use this equation and you want to keep this equation working for you, you have to take theta from the positive x-axis. Anything else is going to change your signs, or it's going to flip which one is sine and cosine. So for the one that we've got in the picture, you would measure theta like this. If we're interested in this one, then we'd measure theta like that. So that's theta 2, for example. Here's theta 1. If we go out farther, theta 3. We can also take this clockwise instead. If we wanted to point down here, that would work just as well. But now that's a theta less than 0. It's a negative theta. If we go clockwise, it's negative. If we go counterclockwise, it's positive, right? Just like in the unit circle. So keep that in mind, right? As long as you measure your theta just like that, then this equation that I have right here will always work for you no matter what. But if you're clever with the math and you know how to do a lot of this stuff and you're very comfortable with breaking these things into components and dealing with all that stuff, you can switch this thing around to what's most convenient at any time, right? But first, if you're still not super comfortable with R hat, which I really don't expect you to be right now, go ahead and stick with this equation. Just remember that theta has to be from the positive x-axis. By the time that you're an expert at this material, you can start to mix this up a little bit more. So, I've got a concept check. Based on this picture, it's just the one single point charge. At which point is the electric field stronger? Our field should be stronger for point A. And let's talk about why real quick. I can do this in one of two different ways. Whether or not the field lines are actually here, right? I don't actually need to have any of the field lines drawn around this to know that point A is going to have the stronger field. Why? Because it's closer to the source, right? It's a shorter distance away from the charge itself. Remember that the strength of the electric field, so just the absolute value, the magnitude of that field, not equal, but it goes with 1 over r squared, right? It's dependent on 1 over r squared. So the farther we get away from that charge, the weaker the field's going to be, right? Whether or not these field lines were actually drawn in here, if this was a negative charge, whatever it is, A would always be the stronger field. Now, if we're basing this off of our picture, we still should come to that conclusion, right? And the reason that I'm going to come up with on that one is because if we look at any of these things, we can see that right around this radius of A, see the distance between these two lines, right? It's kind of a short distance, a little longer than the cursor of the cursor that I've got right here. But if we actually go out to where we're at with B, it is significantly longer, the spacing between the lines. Going off the philosophy on the right here, the closer the spacing between the lines, the stronger the field is. We should expect A to be stronger based on our picture as well. So, another one. 2 protons, 1 electric field. Assume, this was an assumption that somebody pointed out that we're actually making here. Assume that the electric field is much, much stronger than the electric field from either proton, right? Just assume that the electric field is dominating here. There's no proton-proton interaction going on. Or maybe they're at separate times or something like that. Based on this picture, which proton is going to be experiencing the greater acceleration? Here, it is going to be proton A again, right? I promise I'm not just answering A for every single one of these, but it is going to be proton A for this one, and let's see why. We're looking for the greater acceleration. Acceleration, as it's going to show up, is probably best from F is equal to ma. A larger force would mean a larger acceleration. The force determined by Q times E. We know that they're both protons, so they both share the same mass. They both share the same charge. But the lines are much more tightly spaced over on the left side than they are on the right. There's so much space between these 5 over here. And that means that the electric field on the left side is going to be much stronger and weakens out as we get farther and farther away. The field lines in a case like this are not indicative of this, not necessarily indicative of the strength of the field at any one point. It's not stronger on the line than it is off the line, right? They're more just telling us what direction they go and then how tightly packed they are. Because remember that there's still, I could fill in with an infinite number of lines, and we would just expect them to get tighter and tighter as we go down to the left. Right? The stronger and stronger field. This just tells us roughly about where that electric field is going to be going. So proton A should be the greater acceleration here. Another one. Oh no, I didn't delete this answer. Pretend you didn't see that. What are the units of R hat? Kind of spoiled this one already. Unit vectors are very, very special in that they only tell us about the direction. They don't do anything to the magnitude. So, what that really, and the way that we can really describe this as well is that I think I might have shown this to you at the very, 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 very beginning of 191, but it's been a long time if you did see it. A unit vector is defined. So if I was to define R hat, I would take R, regular R vector, divided by the length of R. So what that means is that it doesn't really matter what units I put in here. If I do it in meters, centimeters, millimeters, if I'm really desperate and I use decimeters, whatever I decide to put in here. In any case, the units are always going to cancel out top and bottom. We are going to end up with a unitless value every single time. It's not that the unit depends on the context. It's that a unit vector, if you see any vector with a hat on top, I hat, J hat, K hat, A hat, what's another stupid symbol that I can put in here? Delta hat, which I don't think I would ever see. Any of these things, if you see a hat over top, that means unit vector, that means unitless, that means it is trying to tell you about direction, but it will never do anything to the magnitude of that vector that it's in. Okay, I kind of ruined that one, but that's okay. So, I hit on this last time, and I keep kind of touching on this a little bit and then getting back off of it, but when we started with Coulomb's law, we started by talking about only magnitudes, only a bunch of absolute values, and then when we moved over to the electric field, we started saying, okay, let's introduce this funky thing called R hat instead. But you can still see the general shape of almost everything is still there for the force, right? Almost everything. If I have capital Q as my source of the field, then the electric field would be kq over r squared. To turn that into a force on another charge, little q, I just multiply by little q. And we recreate Coulomb's law, but now we do so with R hat, which arguably this is probably the truer form of Coulomb's law, right? Because this is the actual vector form of this law that we would expect to see. This equation down here does actually account for whether the charges are positive or negative and their relationship to each other, right? Because as it's given, the force would be going along with the direction of R hat. So if both of these are positive, then we do expect a force to be going to the right. That makes sense. If either one of these charges were negative instead, we would see a sudden negative sign when we plug in all of the numbers mixed in here. The direction from R hat would flip. We would expect to see a force pointing to the left at that point, which would be an attractive force, right? And that makes sense. That's exactly what we've been saying about the Coulomb law the entire time. And this is really kind of what I mean when I'm talking about a field is a force waiting to happen. And I've got, I think, is one of my greatest analogies down at the bottom. Forces require at least two particles, right? It's always the interaction between two objects. So it's like partner dancing. You can't partner dance without a partner. Fields, on the other hand, they're everywhere. They have watched every single episode of Dancing with the Stars, like without fail, even the bad seasons. And they have a great expanse everywhere, right? They are waiting for anything to get nearby to start acting on it. And at that point, they're so eager that they'll act on multiple things at the same time, right? The electric field is fantastic for dealing with the fact that you don't always know what your second charge is going to be, or maybe it's a changing second charge, or maybe, and what we're about to see here, you've got a lot of different charges all making a field. How do I find the force then? So far, you've been doing it by hand and finding each of those forces individually, and then once you found each of those forces individually, summing up the components of every single force acting on your particle to find the net force in the end. And so far, I've introduced fields and I've said, hey, look at this. You recreate Coulomb's law, but you have to take extra steps. Isn't that cool? And you said, no, it's not. Here is why the electric field is actually going to be useful. Let's imagine that we have more than one charge. What if we have two charges? What does the field look like then? Luckily for us, there's not anything super crazy that goes on. Fields are additive, which means that if I have two fields, E1 and E2, to find the net field, I just add those two together, right? The values straight add to each other, the components all add up together, it's a bunch of vector addition, but they just add. So I can find the net E field from a group of charges. And that's very nice because what if I threw something like 12 different charges at you? And we had to find the force because of 12 different charges. And then I said, okay, well now do that same problem again, but now instead of 2 nanocoulombs, it's on 3 nanocoulombs, and you would have to redo every single step along the way. Whereas if you're dealing with fields, you can find the field, you can plug in whatever charge you want to, and you can immediately have your net force because of that. It's also a lot easier because you can map out electric fields, whereas with force, you really can't do that. So, let's give it a shot. Let's practice this one a little bit. Let's imagine that I have 3 different charges, right? And I'm sure we've seen plenty of orientations of charges like this at this point, but now we are looking for the electric field at this black dot, not the force on one of the other charges. What is the electric field in vector notation at that dot? And second, what is the magnitude of the field at that spot? Okay, I'd like to start taking a look at this one. And I'm going to have a little bit of a mix of methods in this one. Right, I know I just talked a lot about R hat, but realistically, you'll see why. You'll see why as I start to talk through this thing. But the first thing that I'm going to do is I'm actually going to clean up this thing. I don't want all this stuff here. I would like to be able to use this space, and the picture's already going to be kind of cluttered. So let's go ahead and erase some of these extra bits because, well, we know what the X and Y directions are, right? Maybe I'll add them back up. Here we go. Here's our axes like every good picture should have. So, I'm going to have essentially 3 individual fields acting on this single black dot, right? I am looking for the sum of all 3 of those fields. So I'm going to start by drawing my picture roughly where I expect these points to be going. From Q1, it's a negative charge, so I expect my electric field to point towards the charge, right? Radially inwards. Should look something like that. Call it E1. Q2, I'm expecting this thing to be radially away from the charge, so, and my angle might be a little bit off here, but you get the idea. Going off at some diagonal angle, here's E2. Finally, E3 is nice and easy. It's going along the x-axis, albeit in the negative direction, but it's still pretty easy to follow. So this is the reason why I really don't want to deal with thinking about r hat every single time for all of these things, because for E1 and E3, why bother? Just do the magnitude version. I already know what angle it's going to be. It's more work to deal with r hat, and it's some extra steps and everything. I'm just going to settle with the magnitude. So speaking of that, since I've already got red picked out for me, I'm just going to start with E3, right? And again, I'm just finding the magnitude, not the vector. So that means this is going to be K, Q3. Let me give myself a little bit more space. Let's put some absolute value signs around that. I know it's positive, but it's good practice. Over the distance is 0.04 squared. Right? Fantastic. Wonderful. We have that. We plug in all of the values that we see on our picture so far, and what we should find for E3 is 5.619 times 10 to the 4th newtons per coulomb. Right, and that would be fine, but I do want to have what the vector for this thing should actually be, so what I'll do at the very end is I'll say, okay, now I'm going to turn it into a vector. I see it as pointing in the negative x direction. If it's pointing in the negative x direction, that means that this should be a negative 5.619, 10 to the 4th, I hat. Perfect. We've got it. So now, let's do the same thing, but with E1. Let's see if I can get the darkest version of that one. Oh, and I messed up. That should be labeled E3. I need to make sure that I keep track of those, right? That's pretty important to have. So now we do the same thing with E1. I'm just going to start with the magnitude again because I immediately see it's pointing in the positive y direction. Here, the absolute value signs do matter. 0.02 squared. Should be able to find some sort of magnitude out of this. 1.124. 10 to the 5th. Newtons per coulomb. Right, and then we look at this and we say, okay, well that is definitely in the positive y direction. So it's going to stay positive. But I'm going to tack on a j hat to the very end of it. And we have our second one. Fantastic. So far, so good. Now it gets a little bit nastier. Now we've got E2. And there are two methods to find this, both of which I've already described, but I'm going to walk through both of them for now. Finding E2. Method 1. Kind of like what we used to do with forces. This will be a magnitude first. So kind of like we just solved 1-3, actually. So what I do with that then, I say, okay, well, E2, just finding the magnitude, K, absolute value, Q2, over the distance, 0.02 squared plus 0.04 squared. Squared, please. Thank you. Because remember that the distance away, r, would be a square root. It's Pythagorean's theorem for this one. So if I square r, then the square root gets squared away. So it just saves me an extra step, right? That's all I'm really doing with that one. So I find that magnitude, and what I should find for the magnitude when I actually plug everything in is 4.495, 10 to the 4th. Which is fine, that works out for me. Now what I'm going to need to do is I'm going to need to find some way to break this up into the two components. So I can take any angle, realistically. Since I'm not tied to r hat or anything else, what I'm going to do is I'm going to pick this angle right here. And I'm going to call this one phi. Because it's not theta like we saw from the previous slides, right? So let's call that phi. And then if I just plug in cosine and sine of phi, those are both going to be positive values. But if I look at my picture, I say, well, I know that I should have negative values for each of those, right? It's pointing down and to the left. So negative x, negative y. So E2, at least the x component of E2, will be negative cosine of phi times E2. The y component, same deal. E2 of y is going to be negative sine of phi times E2. Plug in for both of these values. And what do I find for these? So my x component ends up being something like negative 4.021 10 to the fourth. The y component ends up being something like negative 2.01 10 to the fourth. Cool. Now we've got the x and the y components. We can throw that back together into the vector form if we would like. Fantastic. However, you know, it's kind of a magnitude deal, and, well, it's not always the best way to do things. The reason I say that is that method 2 is a little bit more elegant, and oftentimes elegant means more complicated. Packing more things into a smaller space. But it's a good time to practice dealing with r hat and figuring out what's going on with r hat, because realistically, we're going to need to know how to deal with r hat. We cannot do magnitude forever. Next time, you'll see what I'm talking about. We absolutely need to have R2 or r hat under our belts. So, method 2 is use r hat, right? Or r hat. So what I'll do here is I'm going to stay in vector notation the entire time. I'm never going to leave it. I'm going to say E2 vector is equal to k q2, and I don't put absolute value signs around that. That's a very conscious decision not to. Over, it's the same 0.02 squared plus 0.04 squared. That does not change. But now it's times r hat. Okay? And we know r hat from before. We talked about r hat as being cosine of theta times I hat plus sine of theta times j hat, where theta is always, always, always taken from the positive x-axis. So the closest way to get there from the positive x-axis is going to be this angle right here. That's theta, right? And then probably the easiest way to find this one right now, and I'm trying to remember if we have, yeah. The easiest way to find this one right now, realistically, is probably actually to know what phi is beforehand. So we can just say, remember that it's going to be a negative because we went clockwise. It is going to be a negative value, so phi is going to be negative 180 plus phi. Where phi, as I should have listed before over here, phi is, oh, I just had this. Where did it go? Where did it go? 26.56. So that means theta is going to end up being, what is this one? I had this number and I erased it somewhere. Negative 153.4. Let's keep that in orange. And that is actually important because that's going to settle the cosine and the sine being negative for us, right? That'll take care of all of that. We just need to plug this in directly as is. And if we do that, if we're actually checking for these values of r hat, we might as well. Let's go ahead and plug that in. What I should find is that r hat is then 0.894, negative 0.894, I hat, sine of 153.4, negative 153.4 is going to be 0.448 j hat. So now we essentially just take that magnitude, we multiply it by these two values right here. So in the end, we end up doing the same thing, realistically, right? But it's kind of, again, packing it into a tighter space. It's using one line instead of a bunch of different lines, kind of like this. And that's what we mean by more elegant. It looks cleaner, but it's doing the same steps. but it does take care of what's going to be the positive and the negative for us, right? I think that's a little bit more consistent in that regard than dealing with the picture. We have to look at the picture a lot and say, okay, well, this should be a negative and that should be a positive, so let me fiddle with the numbers at the end to make sure that I get that result. Whereas this, we can kind of say, okay, well, I see negative and I see negative. My picture says that's right. So we plug that in, and what we find for E2 is, big surprise, the exact same thing we found for the first method. I should have given myself a little bit more space, so I'll write this one down here. That's what my E2 should look like, right? And that's really the hard part of this problem. So once we have that, we've got E1, we've got E2, we've got E3. We can bring all of that together. I'll do it down here, actually. This one does have to be vector notation. I cannot add magnitudes and call it a day. Do not do that. E1, E2, E3. What we should find is negative 9.64 10 to the fourth in the I hat direction. 9.23 10 to the fourth j hat direction newtons per coulomb. So there is my answer for E total. If I want to find the magnitude of that, right, EX squared plus EY squared, take the square root of that, I find 1.335 10 to the fifth newtons per coulomb, or as I've got it written in Canvas, 133,500. So, that's a little bit longer, right? And I don't necessarily recommend solving out both methods every single time. I really rarely recommend that. Only when you're beginning this stuff, only when you're trying to learn how to deal with a lot of these things would I ever recommend that. Just because it's great practice, right? If I can confirm both methods get me the same answer, then I'm probably not making the same mistake in two separate ways. At least, unless you're me. But I think for most normal people, that kind of validates your answers and it makes sure that you understand how both methods work, right? Because realistically, the R-hat method is a more rigorous method. It's more universal. We're going to see where that has to be the method that we use in a few of our more complicated problems. But the magnitude's just fast. And sometimes we're all about that speed. Dipoles. Right, we might remember these things as the thing that I talked about briefly that said, hey, look what happens when you put a positive and a negative charge right next to each other. They act kind of funky, and then I didn't say anything else about that. Well, now we can say more things about that, and dipoles are very useful things. And you kind of have to take me at face value for that one, because dipoles can often be used to describe more complicated systems. You can use dipole and quadrupole and octupole expansions of things to make very, very difficult problems easier to solve and put it into more common forms. A lot of that stuff, though, is super calculus heavy. Calculus heavy enough that I don't like to deal with it. So it's not really things that we're going to cover in much depth in this course, but the dipole moment is still fantastic for approximating a lot of different things, right? You can roughly describe water molecules as dipoles, even though they're a little bit different from that, but they're better in terms of other things. Maybe off the top of my mind, actually cyanide is a polar molecule that could be used, the dipole moment could be used to describe how cyanide might react in different solutions, stuff like that. But anyways, we did mention that the dipole moment is essentially a positive and a negative charge grouped right next to each other, right? Separated by some distance. A neutral charge, technically, if I sum them up together, but because of that separation, there is a little bit of an electric field that comes from these things. So a useful thing when we're talking about dipoles is what we call the dipole moment, and it's a vector p, and it is not momentum. Same symbol as momentum. There's only so many letters in the alphabet though, and we've already pulled in all the Greek letters and we're kind of running out. So we're reusing p, but keep that in mind. It's not momentum. But the dipole moment, what you're going to do is you're going to take two charges, positive q and negative q. So same magnitude, but flipped, right? Maybe it's 1 nanocoulomb and negative 1 nanocoulomb, or 10 and minus 10, or 500,000 and negative 500,000, whatever it is. They are equal but opposite, and they are separated by a distance s. The dipole moment is equal to the charge, the magnitude of one of the charges, so just one of the q's, times that separation. And the direction is the funky bit. The direction goes against where you would expect the electric field to go. It goes from negative to positive. And the reason for that, I think at least, is because look how we could describe this if we were to actually look at the field of a dipole. So the field vectors version on the left here, I gotta be honest, I can't make any sense out of it. I can kind of look at some of these details and understand a little bit of what's going on with these things, but the thing on the left is a mess. I can't pull any meaningful information from that thing. One of the things that we can look at, though, that is a little bit helpful, you can see that inside the dipole, the charge, or the electric field, does go from the positive charge to the negative charge, right? Which is opposite from what I'm saying what my dipole moment is. But the reason for that, I think, is that because if you're actually looking at these things, you can see that outside of the dipole, it's kind of like this, right? I'm going to draw this separately so maybe it's a little bit less messy. I've got a positive, I've got a negative. My field lines kind of go like this, right? Up and in from the bottom. And so if my dipole moment looks like that, it kind of makes the graph make a little bit more sense. Everything seems to fit a little bit better. And I justify this to myself by saying, well, that's all fine, and it doesn't really matter if it goes opposite the electric field, because realistically, the entire reason that we'd use this in the first place is because we're not looking inside of the dipole. All of these equations that we have that are very special for dipoles are for when we are looking some distance away from the dipole. We have to be way out here for the dipole equations to actually be useful, right? Otherwise, they're not very good at approximations. But anyways, we have two very special equations for dealing with dipoles, right? If we are on the axis of the dipole, so this red line that cuts through both charges, we can say that the electric field is 2 times k times that dipole moment p over r cubed, and that's not a typo. Or if we're on the bisecting axis that splits right through the middle and separates the charges, then it's negative kp over r cubed. And it's an r cubed because we've got a positive and a negative charge right next to each other, and they are counteracting each other. They cause a little bit of an issue. Well, here's a fantastic time to try it out. So, I have an electric dipole, right? It is made from a positive 1 nanocoulomb charge and a negative 1 nanocoulomb charge, spaced by 2 millimeters. It's done in such a way so that the middle is sitting right on the origin. So the positive charge is ever so slightly to the right. The negative charge is ever so slightly to the left. And then I want you to find what is the electric field from this dipole at a point 10, 0? And what is the electric field at a point 0, 10? I strongly encourage you to draw this picture out. Okay. So let's start to take a look at this one. So, as I have strongly worded, please, 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 draw a picture, right? If not for helping solve the problem, for helping you visualize what the electric field around a dipole looks like. Because that's going to be a useful thing. It's going to show up a few times. Dipoles are nice to have. I promise, even if we're not going to use them a ton right now, if you do ever have to deal with a bunch of charges again, dipoles are just going to be useful. The dipole approximation is a fantastic thing. So, what would happen if we drew this thing out? Here's my axes, drawing them nice and large, so I got plenty of space to actually draw on these things. Roughly, roughly, roughly. Can I get that level? Oh, that actually kind of worked. So, now I'm going to zoom way in, because remember, my point is going to be like, point A is like out here at 10 centimeters, right? So my first point is actually way inside of here. All of us are going to have terrible blurry video quality today because, well, we're that zoomed in, right? So here's my positive charge. Here's my negative charge, separated by a really, really tiny distance. My dipole moment goes from negative to positive, right? Just like that. I'm going to draw that a little bit bigger so that we can actually read it once we zoom back out. There's my dipole moment, pointing from positive, pointing from negative to positive. Need to not finish that statement before I get it wrong. So, what does the electric field look like separating away from that thing? Well, kind of like what we saw from last time, the electric field goes in these really, really big loops when we're dealing with a dipole. So I expect my electric field to kind of go out like that, and out like that, and straight out along the axis, and straight in on the other end, and kind of curving in like this, and curving in like this, and we've got these loops, and I'm just kind of willy-nilly drawing a bunch of these things, right? And that's all just fine. Here's all sorts of different field lines for what this thing would look like. And again, length doesn't mean anything here. I'm drawing a bunch of field lines to try and get a shape of where this thing would be. It's going to be strongest close by. It's going to be weakest farther away. So when we're looking at it like this, we can see, okay, well, for point A here, I'm expecting that my electric field keeps going this way. And one of the ways that I could justify this is I could say, okay, at what point, if these are equal magnitude charges, one is not going to overpower the other just based on the magnitude of the charge. One might overpower the other based on distance away, though. Is the negative charge ever going to be closer to my point on the right? It's not. The positive charge is always going to be closer. The positive charge is always going to be giving the greatest contribution. The positive charge is always going to be the one pushing us to the right. We expect our electric field for point A to point to the right. Now, this dipole moment here is given, at least in magnitude, as Q times S. We know that Q for each of these is positive 1 nanocoulomb, negative 1 nanocoulomb. So we say, okay, magnitude, 1 nanocoulomb. I'm accidentally pulling my mouse with my foot. That's causing a little bit of jitteriness on the screen, so I apologize for that. And then 2 millimeters, so 0.002. And there we are. We have our dipole moment, and this should be something like 2 times 10 to the negative 12th. And that sounds a little bit small, but that's okay. We'll kind of deal with that as we have. Once we have that, we can say, okay, well, I'm looking towards my point A here, right? So E of A is going to be 2 times K, or 8.99 times 10 to the 9th, times vector P over R cubed, where R is the distance from our point to the center of the dipole, so that's our 10 centimeters. Right, we plug in all of those values and we should find something like 35.96 I hat newtons per coulomb. There's our answer for part A. Part B, we're looking at something a little bit different. We're looking up here now. And if I follow kind of what goes on with my loops, it wraps around from positive out and down to negative, right? Every single time. I'm always going to see something going in that order. So here, I expect to be going to the left now instead. Right? Going essentially opposite from my dipole moment. And that's why when we're talking about the bisecting axis, it's a negative Kp over R cubed. Plug all the numbers in and we should find something like 18.98, negative 18.98. Don't forget that negative sign, J hat, newtons per coulomb. So, I'll box that in too. Let's make a little bit more space here so that that actually looks clean. But in the meantime, do we have any questions or anything? 8. Okay, that's a little bit cleaned up. E of bj hat. E of bj hat. E of bj hat. I'm not sure which spot you're talking about. Up top here? Somewhere? Oh, shoot. Yeah, you're totally correct. Sorry, now I understand. Yes. Yes, 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 yes. That is what the answer should look like. I don't know my letters apart very well. I feel like there was one more thing I wanted to say. I don't think there's anything else right now. We'll come back to some of these ideas next time in a little bit greater detail. But for now, I've got one last one for you, and we're going to see this configuration of charges a couple times. It's not a super easy configuration, realistically, right? I see it's got a lot of pieces. None of them lie along an axis. This one's a little bit more of a headache to deal with, but it is fantastic practice for an R-hat, right? I really do recommend dealing with this for the R-hat. And furthermore, this is a perfect configuration that if you might notice, I think I had made mention of it right at the very beginning, there is a lab that goes along with today that's essentially playing around with that same simulation that I was showing you guys last time. It is not done on paper. It's not a Google Doc or anything else to download and fill out. It's actually done through Mastering this time around. So you'll see a short little assignment. It's got some multiple choice questions. You'll open up the PhET lab. You'll plug in some things. You'll look at how the different fields go. And it's a fun simulation to play with. It really is. But it shouldn't take you very long at all. You should be able to just, it's helpful for visualizing what's going on with the fields, because as I've been kind of talking about here, the field is everywhere. It's not just at one single point. We're measuring it at one point, but it is surrounding everything. So that's a great way to help visualize that. But one of the fun features about that is that you can take that, and every single one of the charges is plus or minus 1 nanocoulomb. So you can recreate this configuration in the simulation and prove that you get the same electric field at the very end. But for now, that's not the goal. Our goal is to calculate this one by hand. So it's going to take a little bit longer. Okay, so I'd like to start to take a look at this one because it is a little bit of a longer problem here. Right, there's just kind of a lot of moving pieces to deal with. But let's go ahead and I'll get this thing pasted in here. And I want to make sure I've got plenty of space to work on this, so I'm going to put it somewhere like right over here. That'll be perfect. So here is the true optimal use of finally actually dealing with drawing programs and everything else and all the different crazy things we can do with that. I love it. So here's what we've got, though. We've got, honestly, kind of our work cut out for us. I'm going to start with 1 and 2. And there's going to be a lot of different parts of this because none of the points are along an axis with the point, right? Every single one of these is going to have X and Y components, and we've got to deal with all of them. So let's go ahead and get started. So I'm going to go from my charge to my point. Looks kind of like that, and I asked for that to be in black, please. Thank you. Got another plan for blue later. So we've got a line like that, and if we follow kind of what I was saying before of extend that line just a little bit longer, turn it into an arrow, then that's going to be what I will call R1 hat, right, for Q1. So that's great, but I need to know what the angle is, right? So what I'll do is I'll draw my dotted line here, and I'll say, okay, fantastic. This is what I'll call an angle theta 1. And now, what's theta 1? Ugh. And for that matter, what's this R? There's a lot of details that we need, right? So what I can do here is I'm going to draw some triangles first. Because we love our triangles, right? There's part of it. There's another part of it. Now I've got a full big triangle. And we can see in this triangle that this angle right here is also theta 1. So then, one side of the triangle is 0.5. The adjacent side is 3 meters. So theta, there we go, theta 1 is going to be something like, let me actually find this one for sure. So now it would be 9.46. However, from the positive x-axis, I went clockwise. And since I went clockwise, remember, anytime we go clockwise, that's a negative. So theta 1 is going to be negative 9.46, and that's very useful because we can go to R1, and we can say, okay, R1 is going to be cosine of theta 1, I hat, plus sine of theta 1, j hat, if I plug in these values exactly, right? Just right on in, plug in that negative 9.46. We should find the two values being 0.986 I hat, positive, minus 0.164 j hat. And we look at our picture and we say, did it go down and to the right? Yes, it did. Fantastic, right? So our picture agrees with the numbers that we just found, and that's a good sign, right? That's always a good sign. So now what we'll do is we'll say, okay, well, now I know what r hat looks like, and really, I've got everything else I need to find the electric field from point 1, right? So let's go ahead and draw this out. And I'm going to do this in orange. So E1, K, Q1, over. Now here's where it's a little bit funkier. I'm going to do this as 3 squared plus 0.5 squared, right? Because again, that trick with the r and r being squared times r hat 1 specifically, right? We plug all of those things in, and what we should find at the very end is 4.86 times r1 hat. That's the magnitude of that field, and then it gets split up individually to 4.79 I hat minus 0.78 j hat. Perfect. There's E1. Now, E2, we're in luck because this one's actually going to be a little bit easier because we've already done some of the legwork for it. What I can do is I'll trace my line and I look at this and I say, hey, would you look at that? I made the same triangle, right? Just flipped over now. So what that basically means is that if I'm thinking about R2, or R2 hat specifically, right? It's the same angle. Theta 2, just going counterclockwise now, is going to be positive 9.46 degrees. And if it's positive 9.46 degrees, that means I don't even have to recalculate these individual values either. What I can do is I can just say, R2 hat is going to be 0.986 I hat plus 0.164 j hat. Makes that whole thing a little bit easier to deal with. So I can say, let me do it up here. Now E2 is going to be K Q2 over, same thing as before, should have this as 3 squared plus 0.5 squared times R2 hat. Now, here's where it's going to be a little bit different. R2 is already found to be positive in both y and x, but the sign of our charge is negative. So r hat never cares about the sign of the charge, right? R hat is always determined from where the charge is to the point that we're looking at. That's what r hat is telling us. The sign of the charge will tell us whether we need to flip that or not. So here, since we're plugging in negative 3 nanocoulombs, what we're going to find is that our magnitude right before we plug everything is negative 2.92 times R2 hat. Or go ahead and plug that in, and we should find negative 2.88 I hat minus 0.48 J hat. And that's where the negatives come from. And then we look at this thing and we say, okay, let me check all of these things real quick. I expected my positive charge to have an electric field radially outward like this. Positive x, negative y. It is. For my negative charge, I expect it to be radially inward like this. Negative x, negative y. It is. Fantastic. Right? Our picture agrees with all the math that we just plugged in, and that's a good sign, because if those don't agree, well, something's wrong somewhere. So now, we've got all of that stuff. Here's the problem. My picture is already way too messy to look at and see what's going on. Right? There's a lot of things going on here. I'm not going to try and complicate this any further than it already is. So what I'm going to do is I'm going to take advantage of the fact that I'm on a draw pad. If you are not on a draw pad, you might want to draw a second picture. That might actually be really useful. Because what I can do now is I can just get rid of all that stuff. And I can say, okay, now we're just going to focus on 3 and 4. So 3 and 4, kind of in a very similar manner. We go from here to here. The arrow, and you have to imagine that the arrow actually lines up with the line I just drew. Looks like that now. So there's my R3. Now I've got a new angle. It's not quite the same as before. This is what I'll call theta 3. And I do a similar thing as last time, right? I say, okay, well, here also is theta 3. I see I've got a big triangle where one side is 0.5 and one side is 1 meter. If I plug in all of those things, I should find my theta 3, because it's going clockwise, negative 26.6. Right? So R3. Plug in all of this stuff. R3 I should find and I'll go ahead and write out this stuff again. As long as I always take my angle from the positive x-axis, I can always take this trick of just using R hat that looks like this. Next time I'm going to shake this up just a little bit, but until then, I'm just going to stick with this. So I plug in those numbers, and what I should find now is kind of similar, but a little bit different. In a case like this, I have positive 0.894 I hat and negative 0.478 J hat. Right? And it does indeed point to the right and down. So perfect. That all makes sense again. Where was my line from last time? Somewhere around there. So let's put E3. Hopefully this doesn't clash with anything I wrote before, but that's okay. I know some of the stuff in purple already is all over the place, but I'll deal with that later. I'll move some of those things around. So E3, I plug in all my stuff, right? Again, I don't bother with any absolute value signs because it would actually mess up my numbers here. I need the negative to be negative if it's going to be. Plug in some numbers. I should find an absolute, or not an absolute, a magnitude of 14.33, negative 14.33 times R hat, which when split up evenly should be something like negative 12.81. I hat plus 6.85 J hat. Right? And does that agree with what I expect to see? Well, should be going radially towards, and this is not a good angle that I'm proficient with drawing, but I see it going to the left, so that's a negative x and a positive y. I see a negative x and a positive y. Fantastic. My numbers agree with my picture. We've got that one. And then I can make the exact same arguments again for Q4 to say, look at that. It's another triangle. Right? What a surprise. Theta 4, I ask that to be in purple, please. Thank you. Theta 4 should be a positive 26.6 degrees. I'll go ahead and draw it in. Why not? Just like that. Right. Plug in all of my numbers. And again, in the same way, I can say that R4 hat, because it's the positive version, the cosine does not change. But the sine does. Right. These shortcuts that we get to take along the way that make ugly problems at least a little bit more bearable. Get all that stuff. We plug in a magnitude. We should get a positive 28.66. Plug in all those things. 25.62 I hat. Plus 13.70 J hat. Our picture would suggest going radially away, pointing up like that, positive X, positive Y. Our answer agrees. Fantastic. At the very least, the signs agree, right? And if the signs don't agree, then something's probably wrong with my picture. But as long as the signs agree, that gives me at least a little bit of validation before I go into this all the way. So then we bring everything back, right? And now, as long as we don't look too closely about what's going on in the purple, we have all of our values right in front of us. So we can say at the very end, E net, sum all of these things up together to look something like 14.79 I hat plus 13, just kidding, plus 19.29 J hat. And that's what we end up with, right? And we can kind of see where that might be coming from. Right, some of the stuff is going to be reversed, but we've got a few things that are really strong pushing up in the Y direction, and then other stuff pushing in the X direction. So that all seems to make sense to me. That feels like a valid answer. But this is kind of a longer one, right? But I do encourage you to practice things like this because our hat is just going to continue being here for us. We've really got to be able to learn how to deal with it. So I do recommend it as good practice, even if this one is probably a little bit harder than some of the other ones you're going to have to do for a little while here, at least until next lecture. Yeah, that's kind of an example of how we take care of all this. I think we will end 23-1 with that. I know it's a lot of kind of review from the last time and kind of just growing on some of those topics a little bit more, but next time we'll dig a little bit deeper into this multiple charges idea and get into continuous charges where we'll start to have some real fun with the math. But until then,